All right, hi everyone, welcome back. I hope your exams went well yesterday. I'm just going to go ahead and jump into our content for this week, which we're going to talk about what you guys discussed yesterday, and then jump into a little bit of tomorrow's in the following lectures. So the first question that I have is, what are the steps of protein sequencing? And I copied down what's in your professor's notes, but I also included one that I think is a little bit easier to conceptualize without all the specific details. So the first step is separating covalently linked chains. So this is stuff like hydrogen bonding that's putting a structure together. This is stuff like your alpha helices, beta sheets, your secondary, tertiary, and quaternary structures. Okay. However, disulfide bonds are covalent bonds, and that's why there needs to be a separate step for them that says to block and break disulfide bonds. Okay, so that's the second step that we have. The third step in protein sequencing is to cleave the proteins and peptides using proteases and chemicals, then isolate each of those individual peptides of the protein and sequence them. That's 3 through 5. And then you're going to repeat steps 3 through 5 with multiple different proteases and multiple different enzymes until, as it says in step 7, you can assemble the full sequence. Okay, so this is what your professors have, and this is the more thorough explanation. However, down here I wrote one I think is a little bit easier. And that is, first you break the non-peptide bonds, okay? So all that's going to be left, so this is steps 1 and 2 basically. So this is basically just primary structure, okay? Next, you're going to cleave and sequence the peptide fragments, okay? So this is, again, steps 3 through 5. You're going to cleave them using the various proteases and then sequence them, and then repeat that with the various cleavages from proteases and chemicals, and then put together the sequence. And I think this is a little bit more conceptual and a little bit easier to understand in our heads than all of the steps that are shown above, okay? The second question that I have prepared is, which of these methods is not effective at separating non-covalently linked chains? So non-covalently linked chains is telling me secondary, tertiary, quaternary structure. Well, I know that pH can do that. I know that high salt can do that. And I know that chaotropes, and I apologize, I'm not certain how to pronounce that name, which are chemical denaturants. An example of this that your professors use is, excuse me, it's ammonium, sorry, I just want to make sure I have it right. I'm sorry, it's not ammonium, it's urea, excuse me. So something like urea. And then finally, reducing agents. Reducing agents don't actually separate non-covalently linked chains. So reducing agents is the actual answer to this question here. Okay. Number 3, which amino acid usually forms disulfide bonds and what kind of reaction is it? So looking at our amino acids, methionine and cysteine both have sulfur in them, so that's not really going to help us too much, but think about the structures of them anyways. So methionine, I know, has a CH2 group, and then a sulfur, and then a CH3, right? And it's got other stuff over here, but this is the thing that I want to focus on. Whereas cysteine has a CH2 and then SH, okay? And so the answer, the amino acid, we haven't gotten to the answer yet, acid is cysteine. And the reason for that is because cysteine is acidic. So when it loses this hydrogen and becomes S minus, that S minus is free to bind with another sulfur. Whereas the sulfur in methionine has lone pairs, but it's relatively stable, and so it doesn't want to form those reactions. And that's why cysteine is most likely going to be the amino acid. Can methionine form these disulfines? Yes, but usually it'll have lost that methyl group first in order to do that, okay? And now, is it an acid-base reaction or an oxidation-reduction reaction? So if it were an acid-base reaction to form these bonds, it would be something SH, and we'll say 2 of them, and that's going to go it's going to release its protons and then bind to something else that's got protons. It doesn't really work as an acid-base. As a redox reaction, on the other hand, if your sulfur, SH, we'll just leave it there. If we give it 2 protons and 2 electrons, what's going to happen is those 2 protons can pull away the hydrogens and leave each with a single electron rather than 2, and then those 2 electrons will help form a disulfide bridge. Okay, and for that reason, the answer to this is D, an oxidation reduction reaction. So I want to come back to 2 for a moment and discuss why I put reducing agents as that wrong answer. The reason is because you need reducing agents to break your disulfide bonds, okay? But your disulfide bonds are your covalently linked chains. So you can use all 4 of the responses in number 2, but you can't use them all for the non-covalent stuff. You need the reducing agent for a covalent bond that you're breaking, okay? And I hope that made sense. If it doesn't, please feel free to type it in the chat, okay? The next question, number 4, draw the cleavage of trypsin in the peptide AT. Okay, so I did include this image right here to the right because these are your protease enzymes. There's trypsin, V8 proteases, chymotrypsin, pepsin, and thermolysin. You also have chemical cleavage, or I don't know exactly if they're still called proteases. They're just, yeah, chemicals that can cleave as well. This is things like cyanogen bromide, and depending on your professor, you may have to memorize some or all of these. You may have to memorize some or all of the chemical denaturants. This is I'm sorry, not chemical denaturants, chemicals that cleave, excuse me. It really is just dependent on your professor, but I wanted to do an example because I think sometimes these can be a little bit confusing as to what we're trying to cleave. So in this example, we're using trypsin and we cleave on the carbonyl side of arginine or lysine, okay? So over here we have alanine, well, it's not going to cleave there. We have arginine, we have tyrosine. So it's going to cleave at arginine, okay? So I very briefly want to draw this, this peptide, and then I want to show where it's going to cleave. So the first thing is alanine, or actually the first thing should be N-terminus, and I'm just going to assume a pH of about 7 since that's neutral. There's central carbon, you're going to have hydrogen here, and then double bond to the nitrogen, so there's our peptide bond. Alanine has a hydrogen as its R group. This is the N-terminus of arginine. Arginine has central carbon, hydrogen, and then I believe it's 1, 2, and then a nitrogen, double bonded to a carbon, which has 2 more nitrogens. Or actually, I don't know if that's, I might have one of those wrong. I need to double check that, I apologize. There's our nitrogen, and at this pH, actually, this should be protonated, so that's plus. And then we're going to go draw our peptide bond again, and next to threonine, I'm sorry, I believe I said tyrosine before as well, correct, threonine, and this is going to be O minus. Okay, so threonine's R group is OH and a methyl. Okay, so excuse me, so there's our peptide, and according to this information that we have over here, trypsin cleaves at the carbonyl side of arginine, in this case, or lysine. So our arginine, let me change colors to make sure that I'll highlight it. So our arginine is starting here, this is its N-terminus, going to here, okay? So we don't know the exact mechanism of this, and I don't believe you ever need to know the exact mechanism for the purposes of Biochem 1, but it's going to cleave somewhere around right here, okay? We don't know exactly what it's going to do, we don't know exactly what charges anything is going to have, but that's that side of cleavage, okay? Does that make sense? Or rather, does anyone have any questions about that? Okay. If you do, again, feel free to type them in the chat. I'm just going to go ahead and move to number 5 since I don't hear anything. Okay. From which side do the Eggman degradation and carboxypeptidases sequence respectively? Excuse me. So we use these two, the Eggman degradation and carboxypeptidases, to help us sequence our peptides once we've cleaved them so that we can put things together. So they don't both cleave from the N-terminus. I wanna start that off very clearly. They cleave from opposite sides, okay? And the sides from which they cleave are The Eggman degradation is the N-terminus, and carboxypeptidases are the C-terminus. So I want us to go back to number 1 again. Your professors tell us this in number 5 of number 1, or I guess in number 5 of the steps of protein sequencing. So by remembering this, you can answer that question a lot easier, okay? One important note is that these two also have different mechanisms. So the one that's really talked about in your slides, from my understanding, is the Eggman degradation. So I very briefly want to go over that while we're here. So what's going to happen with the Eggman degradation is, so we're going to have this peptide that's this long, and we've cleaved it into various parts through the past steps that we've done, and now we want to sequence this. So to sequence this, we're going to start at the C-terminus, okay? We're going to bind, immobilize the peptide, I believe is the term that's used, at the C-terminus. So if this is the N, then this is the C-terminus. This is where it's going to bind to this matrix that we use. And then from there, you're going to bind the Eggman reagent, which is a phenyl isothiocyanate. Excuse me. I know it's a long word. I don't think you need to know all the details, but you bind it to produce what's called a phenylthiohydantoin derivative, and then that gets detected at various absorbances. Okay, so what happens is, since the C-terminus side is bound, you start at the N-terminus, and you're going to identify this first one because of the UV absorption of this PTH derivative. Every amino acid is slightly different. And so because of that, in my first round of Eggman degradation, I figure out, hey, this is a tyrosine. Excuse me. In the second round, I think this is a serine. And then in the third, and so on and so forth, until I've identified this entire chain, okay? And yes, it would be incredibly tedious to do every single amino acid, because then you might be doing 500, 600, 700 cycles of this Eggman degradation. And so there are some systems that can do maybe 50 at once. And so it's a little bit quicker, okay? Carboxypeptidases aren't really discussed too much, so I don't know the exact mechanism, but the general thing is that they cleave the C-terminus amino acid, and then the way that the residues are detected isn't really talked about, but you can detect them in the order that they appear. So the first thing that you detect, because you're doing this as the peptidases are reacting, the first residue you detect, let's say you see a tyrosine peak, you know, hey, the first thing on the end is tyrosine. The second thing you detect is going to be serine in this case, with this example made. And so you're going to see a peak for serine in whatever absorption or whatever it is that you're using until it finishes. There are also 2 carboxypeptidases. Again, I'm not certain how important this is to know because this is really detailed, but if your professor asks, I'd rather have covered it than not. Carboxypeptidase A prefers aromatic or branched amino acids. So your aromatics are tyrosine, tryptophan, and phenylalanine. Your branched would be something like valine. It would be something like threonine. Okay, and carboxypeptidase B favors your basic residues, which are arginine and lysine, but it specifically prefers that they be positively charged. Okay. And I'm just going to go ahead and take a break for one moment to get a drink of water, and then we'll move on to number 6. Okay, so given the following cleavages from 2 different enzymes, assemble the correct sequence. So this is, in my opinion, one of the really fun parts of this section, because it's almost like putting puzzle pieces together, except you're doing it with enzymes, which is kind of interesting. So what you guys see here is, let's say, I don't know, I did a trypsin cleavage, and that's where I got this first one from. And then the second one, maybe I did chymotrypsin, or maybe I did pepsin, or whatever else. And what you see happening is L, I, Q, and K, and this is how I suggest solving these, is just find 2 that fit together, and then build from there. So in this case, we find L, I, Q, and K. that fit together. I know that the next thing is going to be A, okay? So I have 4 choices for where I can find that A. It might be here, it might be here, it might be here, or it might be here, okay? Now, yes, usually it would be the first ones, but they might have given them to you in the wrong order. They might have, put them backwards or something to trick you. So just keep that in mind, that maybe the sequence is backwards for whatever reason. In this case, it's kind of obvious that this is the A we're looking for, but if this E were also an A, what we might do is compare the second amino acid in the sequence and see arginine versus leucine. Okay, arginine is next. And so I'm just going to go ahead and draw a line between K and A. Okay. The next thing I can do is I can actually fill in a little bit more than into my second cleavage because of my first cleavage, because I know A, R, D are next. But I also know that T has to follow because of cleavage 1. So T comes here. Okay. And in enzyme 2, it's a little bit easy to see. There's only one T, so this would just be D to T, right? But you could be getting them in, again, it could be backwards. You could be getting multiple sequences. I could have given you enzyme 1 out of order. I didn't, just because I thought it would be simpler to just go through it in order. But yeah, it's all fair game. So now, going through this multiple choice, it's really important to be mindful of, not picking the wrong one. So it's LIQKARDTELSDK. Okay, great. So it's A. One thing that I think is really helpful is to count the number of amino acids you have. I would count, at the end of enzyme 1 cleavage, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And in enzyme 2, you have 13, whereas B and C aren't 13. And so that might be a really helpful way to cut out a couple of those answers if you're really running short on time. Okay. Number 7, which mass spectrometry method breaks proteins into smaller fragments? So I'm going to start off right away and say C and D are not mass spectrometry, excuse me. So all that's left is ESI and MALDI. So I'm going to ask, if you know, go ahead and type it into the chat. Which one is it that breaks proteins into those fragments? All right, so the answer to this one is ESI, and I'd like to talk about both of them in a lot more depth over the next 2 questions, and that's why I have them. So MALDI it stands for Matrix Assisted Laser Desorption Ionization, and there's a slash. Let me write it out. I don't believe you need to know what it stands for, but I think that having it can be more helpful sometimes. Desorption / ionization. Ionization. Okay. So what happens here is I have this long protein, and I introduce a proton, H+. Okay. And it floats around this protein and gives it a single positive charge. Okay. And that's the difference between MALDI and ESI, by the way. They both introduce positive charges, but it's the number of positive charges, and it's whether they cleave or not. So this is the first big difference, is that MALDI introduces, and I want to put this over to the left side, 1 proton only. And no cleavage. So this proton can kind of go anywhere it wants. If the N-terminus isn't protonated yet, maybe it'll protonate that. If there's an arginine or or any of those other basic amino acids, lysine or histidine maybe, it can go ahead and protonate one of those. Doesn't really matter for the purposes of this course which specifically it's protonating. What matters is what we get out of it. So mass spectrometry is usually on the y-axis. This is a percent abundance or something like that. Abundance. On the x-axis is usually m to z. In other words, mass to charge is on the axis, m to z. Okay, so if I have a single positive charge, effectively what my MALDI mass spectrometry is doing is telling me to compare by mass. So I get a peak here, and I apologize for the peaks being a little bit less than perfect, and these are various proteins, then I can tell this is my heaviest protein, this is my second heaviest, this is my lightest. I'm sorry, I have that backwards. This is my lightest protein since it's got the lowest M to Z ratio, and this is my heaviest. Excuse me. And then this one is just in the middle. Okay? And so what MALDI does is it gives us a single positive charge so that it can be detected by the mass spectrometer, and then it just lets us evaluate things by mass, which is awesome. It makes things a lot easier, but what if we don't just care about the mass? What if we want kind of a little bit more exact than that? What if we're looking for, rather than, oh, I know that the relative masses are these, what if I want to know the exact masses? So this is where ESI comes in, and ESI is brilliant. So ESI stands for electrospray ionization, and this is where I think most of your problems are going to come from. Electrospray ionization. So because this is a spray, it shoots out a ton of protons. So in this very same protein, you're going to get A's all over, and they're all going to come in and protonate something. And some of those protonations are going to cause cleavages. So this protein could be split into a fragment here, and a fragment here, a fragment here, and so on. And they're all going to be positively charged, but they're going to have different positive charges. They're not all just going to be a +1 charge. Okay? And so let me write that over to the side. Multiple protons and cleavage. So in this very same mass spectrometer, what you'll get is, once again, M to Z and abundance. There we go. Now, instead of these being different proteins, this will be fragment 1. And this will be fragment 2 and 3, and so on and so forth. Okay? And a lot of times what's going to happen is each fragment will differ by a single proton. Okay? They sometimes call them different names, but in general, it's usually just a single proton. And I want to try to make sure that I get the name right for this. So I'm going to come back to it once I'm sure that I've memorized it. Okay, so let's do an example of an ESI, since I think ESI is probably more confusing. So a proton was put through ESI mass spectrometry. 2 peaks emerged. The first peak was at this, the second peak was at that. What is the charge, and then what is the mass? So we're going to start off by making a couple of assumptions. The first assumption we make is that these 2 peaks are 1 proton apart. Okay? So what that means is, excuse me, is that the series, so really what you're going to get, and I want to go to number 11 because this has an example, is a ton of different peaks. But what we look at is 2 peaks with, 18 and 17 protons, or 13 and 10 and 12, or something like that differ by 1. And so we can assume that, and just for the sake of convenience, I'm going to say x1 and x2, okay? So I'm going to ask a question that's a little bit weird. Is the larger number going to be, or actually, let me reword that. So now we need to figure out, so 842.7 and 912.3 are our M to Z ratios. But they're a little bit, we can write that out differently. So I can write out that Z is just going to be the number of protons that we have, right? Because each proton has a +1 charge. So really it's Z times +1, but it's just Z because 1 times anything is just that thing. All right. The next thing is our mass. Our mass is going to be the mass of the protein, which I'm going to use as big M, but it's not just the mass of the protein. It's the mass of the protein plus the number of protons, because each proton has mass, and it's got about 1 atomic mass unit, or 1 Dalton. And since we tend to do these in Daltons, we have to include the mass. Okay? And if these two numbers differ by 1, the 842 and the 912, if they differ by a single proton, then I know that if this is the equation for one of my peaks, x1 or x2, then the other one has to be m plus z plus one more proton divided by z plus 1, because that's an extra proton. Okay? Does that make sense? Or rather, if it doesn't make sense, please ask. This is one of the more complicated parts of this section, and it's not fun math, but unfortunately it's math that we have to do, so I want to make sure that it's like really good in your heads. Okay? So I don't see any questions, so I'm going to go ahead and move on. So now we have to figure out, is the m plus z over z or the m plus z plus 1 over z plus 1, which one matches with which? Okay? And I think that the natural reaction is, well, this equation on the left has plus 1s, so it's got to be the bigger one, and let's assign 912 to it. That is not the case. Okay? So this equation is the smaller peak, always. And the reason for that, and I want us to try this, so if you guys have a calculator, go ahead and get them out. Our masses are going to be something like, I don't know, 10,000, 30,000, 40, 50,000 even, Dalton. And our charges are going to be somewhere around 100. Okay? So if that's the equation that we use, I'd like to see what we get out of it. And then I'm going to do the exact same one plus 100 plus 1. And I'm going to do that same 100 plus 1. Okay? And so 10,000 plus 100 plus 1 divided by 101 is about 100.001. Okay? I don't know if you guys are able to unmute yourself, so if you have a question, feel free to type it into the chat. But I do see that hand raised. I don't want to ignore you. While you type that in, I'm going to go ahead and do 10,100 divided by 100 is just going to be 101. Okay? So we see here 101. That this equation, despite being what we would see as a smaller equation, gives us the larger number. Okay, and so we need to be mindful of that and do that. Okay. Oh, these aren't actual numbers. This is just an example to show how, or to show kind of why the smaller equation tends to go with a larger number, and the larger equation goes with a smaller number. So I just wanted to kind of prove that point. Because it's something that I personally really got confused on, and it's something I know is kind of a popular question. But no, thank you. That was a really great question. So let's go ahead and actually do this math. Okay. So, and I'm gonna. I think I can just. Hang on. I think if I do that, hang on. I can erase them so that we have the space to keep writing. Okay, so we're going to go ahead and set these as 912.3 equals m plus z over z. 842.7 equals m plus z plus 1 over z plus 1. Okay, these are very tedious, so I'm going to go ahead and just start solving. We're going to multiply both sides by z. And I already wrote it wrong. 912.3 times z equals m plus z. We're going to subtract 1 z from each side to get 911.3 z equals the mass. And I want to set both equations equal to mass so that I can eventually solve for it. 842.7 times z plus 1 equals m plus z plus 1. I'm going to go ahead and subtract z plus 1 from both sides to get 842.7 z plus 1 minus z plus 1 equals mass. And then from there, I can just go ahead and clean that up to get 841.7 z plus 1 equals the mass. Then finally, we're trying to move us a little bit over to the right so I have some more space. We can set our two equations equal to one another to get 911.3z equals 841.7, and this time I'm going to distribute them out. Z plus 841.7 we're going to subtract 911.3 minus 841.7 to get 69.6Z, 9.6Z, and that's going to equal 841.7. So we're just going to divide the two. 9.6. And then the number we get out of that is Z equals 12.09. Okay, great. So our charge is 12.09, isn't it? Well, no. So it very well could be 12.09. We have to remember how these charges are being introduced. These are protons. Protons don't give us like a tenth of a charge, half a charge, anything like that. They give us full charges. And so despite the number being 12.09, we approximate that, we round it to the nearest actual number, simply because it has to make sense. So the charge, and we have to list it, the charge at the, let's see, we solved for Z. So Z is the charge at the 912.3 peak. So the charge at 912.3 equals plus 12, right? And we can also say that the charge at the 842.7 peak is plus 13 for the exact same reason, except we know it's just Z plus 1. Okay? Now, what is the mass of this protein? This one is a little bit easier, thankfully. We can just take this equation, plug Z in, and solve for the mass. I'm just going to go ahead and do that here. So 912.3 equals m plus 12 over 12. Don't know why that table just formed. Is always a smaller number. Okay. Larger number equals. So keep in mind that it's not the larger number. It's the larger number minus 1 times Z. Sorry, let me switch back to my OneNote so I can actually shift. So, right, I think if I circle this, I can kind of show it a little better. Right here, we said it's 912.3Z, which is the larger number times Z, and then we subtracted 1Z from it. And so it's kind of larger number minus 1 times Z equals smaller number minus 1 times Z plus smaller number minus 1, if that makes sense. I hope that's clearer. But yeah, generally you can conclude that that's kind of how they'll fit together. And for the sake of not having to repeat larger number and smaller number so much, we abbreviate them X and Y. Excuse me. Generally, X will be the larger number. So this will be X and this will be Y. Okay. But yeah, the trend is fairly consistent, that it's going to be something along the lines of X minus 1 times Z equals Y minus 1 times Z plus 1. Okay? Does that make sense? Okay, awesome. So coming back to this solving bit, we're going to take 912.3 times 12 minus 12 to get 10,000, or sorry, M I should say, is 10,936 Dalton. Okay, so putting that over here, we're going to say that the mass equals 10.9 kilodalton. Okay, that's a very, 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 very tedious procedure. I don't love doing that. So there's another formula that we use, and I think your professors have probably shown it to you, but I'd like to go through the derivation because I think it's important to understand where it comes from. And basically where it comes from is by setting these two equations equal to each other, m plus z over z, and then y equals m plus z plus 1 over z plus 1. And again, x is your larger number. Larger number. Okay? So we're going to go ahead and solve for m in both cases to set them equal to each other. And if you have any questions about like where I maybe got something from, if I skip a step or like just don't show it, please let me know. Plus y minus z minus 1 equals m. Okay, and I'm going to go ahead and set these two equations equal to each other. And I apologize, I know that I write crooked. Xz minus z equals yz plus y minus z minus 1. Okay, and now I'm just going to put all the z's on the left, everything else on the right. So xz minus z minus yz plus z equals y minus 1. And then I have a plus and a minus the charge, so those cancel. I'm left with xz minus yz equals y minus 1, y minus 1. Y minus 1. I'm going to factor equals y minus 1, and then divide to its overall formula of z equals y minus 1 over x minus y. And again, x is the larger number, okay? So I have this other example that I want us to use in order to kind of use that easier formula to show you guys the difference between the work, okay? So this one is asking us for the charge on myoglobin at x1, and then the mass of, oh, we got a question, 1 second. Can you show that screen again, please? The work, this part? Okay, sure. And just let me know whenever you're done. Okay, awesome. So we're going to go ahead and use this equation to solve this question, since I think it's a little bit easier, and hopefully it'll show a little bit more of why you're given this equation. So it wants the charge at x1, and I don't know if you can see it very well at the bottom. The lighter mass is x2, the heavier mass is x1, and they just do that for whatever reason. I don't know, they want to. Coming over to this left side, we know that x is our heavier mass. Sorry about that. So we're going to say z is equal to our lighter mass, which is y. So 942.8 minus 1 divided by 998.2 minus 942.8. Okay, so just to clean this up a little bit, we're going to get 941.8 on the top, and then 55.4 on the bottom. Okay, and when we plug that in, you get 17. This number was a bit more exact because I think this is a question from a textbook, so it was a little bit smoother, but we get 17. Okay, so we know that the charge z is equal to 17, but they want the charge on myoglobin at x1. So let's make sure that we actually have that. Okay, so x1 is our heavier one, which is x. X equals m plus z over z. Okay, so yes, we do. If they had asked for the charge at x2, the answer would be 18. Okay, and is everyone okay with why that is? Okay, awesome. So now B is once again the mass of myoglobin. Oh, I skipped a lot. Okay, I apologize. Okay, so the mass of myoglobin is a ton easier now because we can just take this formula that we've been using and plug in x. So x is 998.2. 998.2 equals m plus 17 over 17. 17 minus 17 is going to equal about 16, about 17.0 kilodalton. There's my mouse. That saves a ton of time by just using that easier formula, but I just want to make sure that I emphasize the easier formula comes from those other two formulas that we figured out just based on the concepts. And, you know, just keeping in mind just where they all come from, okay? Does anyone have any questions about ESI mass spec before we move on to MALDI? Okay, awesome. So number 12. So given the mass spectrometry results for various proteins, we're going to rank them by mass, okay? So we don't really care about the y-axis in this case, we care about the x-axis. And the x-axis, remembering, is the M to Z ratio. And with MALDI, these are each about a +1 charge. Okay, there are a few exceptions like the cytochrome over here, but we're just going to treat them all as a +1 charge. Okay, so this means that the mass of myoglobin, and I'm just going to round this, is 17,000 is the M to Z. But again, Z equals 1, so the mass is going to equal 17,000. Okay. For cytochrome C, I'm going to just say 12,500. And again, that's going to be the mass. Ubiquitin, 8,500, I think, which is once again the mass. And cytochrome, this last cytochrome is 2+, so this one would actually be somewhere around 12,000. However, because MALDI almost always introduces a single charge, I'm going to show it as 6,000 just for now, just so that we get in the idea of what MALDI is, and then we're going to talk about the way it is in this specific case, which is a little bit weirder. Okay, so regular MALDI. Regular MALDI, the heaviest is going to be myoglobin. And then cytochrome C, and then ubiquitin, and then finally just this cytochrome. Okay, now this last cytochrome is one of those weird exceptions where it does have a +2 charge. So in this case, Z equals 2. And since Z equals 2, we need to double this number to get to about 12,000. Okay? And so 12,000 is going to put us, and I know it's not exact because this is a little bit over 6,000, and cytochrome C is also a little bit over 12,000. But I'm just going to, for the sake of making it a little bit easier, since we don't have exact numbers, I'm going to put it about there, about at 12,000 exactly. So now our new ranking with this, when you have an exception is going to be myoglobin, and then cytochrome C, and then the regular cytochrome, and then ubiquitin. Okay, does that make sense? Okay, so I'm going to go ahead and move to number 13. What type of structure is a disulfide bridge? And this is one of the, so these next three questions, by the way, I should mention, are kind of working ahead a little bit because I didn't just want to repeat an entire lecture because you have that in class anyway. So I wanted to work ahead a little bit so that this session would be a little bit more interesting. So what type of structure is a disulfide bridge? This is one of the most difficult questions, and this is one that you know, students hate. I hated this when I first learned it. I still kind of do, to be honest. Professors, I think, just kind of I don't know if anyone is really thrilled by this. The answer is primary structure. And the reason for this is because, as we mentioned, your disulfide bridge is a covalent bond. And when we say your primary structure is just the peptide bonds, really, we simplify that because peptide bonds are usually the only covalent bonds in a protein. However, the disulfide bridge is the exception to kind of all the rules. Since it's a covalent bond, it is technically a part of your primary structure. And I know that it's unintuitive. That's why sometimes you'll see something like this in your primary structure, and this is a disulfide bond. And the reason for that is because this does count as a primary structure, whereas your alpha helices, your beta sheets, all those aren't going to show up. Your disulfide bridge will, okay? All right. So number 14 is one of the more interesting concepts that we talk about in the next section, and it is phi and psi angles, okay? So in your various peptides, we talk about phi and psi angles as basically your phi angle is the angle between the nitrogen of the N-terminus and the carbon of the central carbon of that same amino acid. So in this example, we have the one that they had as the phi is the nitrogen to the central carbon. However, this is another central carbon and this is another N-terminus. So this is, excuse me, another phi angle. This is a phi angle, and so on and so forth. So these phi angles are fairly common, or every amino acid has one. And psi angles are the same, except between the central carbon and the amino acid C-terminus. So this would be a psi angle. This is obviously a psi angle, as the one labeled, and then this is also a psi angle. Okay. So there are applications of this, and the next bit, the Ramachandran plot, that's what's below. Before I talk about it, I want to kind of explain why this is significant. So by understanding these angles, we can learn a lot about a protein's secondary structure. Okay, and that's what the Ramachandran plot shows. And I kind of spoiled it because that's what this very last question is. It doesn't tell us which amino acids we have, where they are, or how many there are. It tells us which secondary structure we have. Okay, and so that's kind of the answer to that. And this is what the Chandran plot shows. So it's a measure of phi to psi, so one bond angle to the other bond angle. And depending on what they each are, these 3 or 4 spots that are kind of yellow are the various secondary structures that are fairly common. There are, if you looked one up right now, a Ramachandran plot, you would see some that are labeled and show this is an alpha helix, this is a beta sheet, this is, you know, anti-parallel beta sheet, this is these various things. I just wanted to introduce this concept because I think that it's one of the ones that's most confusing. So I think by just kind of showing it at first, you can hopefully get into the practice of seeing it. But that's really all I had for today. There wasn't too much to talk about. And if I got too much into tomorrow's section, it would just be a ton of memorization. And I thought it would be better or more appropriate next week. If you have any questions, feel free to type them in the chat. Let me know, just anything like that. That's this week's review. What does each region represent in the graph? Sure, it's a great question. I guess we can go into it in a little bit more depth since there's so much time. Excuse me. So, generally speaking, let me scroll up. Okay, there we go. So, this area over here, this really big area, is beta sheets. Beta sheets. And I don't know the exact breakdown, but this has both parallel and anti-parallel. Plus anti-parallel. And I'm gonna go into a little bit more depth as to what those both mean. I just want to very briefly introduce them. The area beneath, so this kind of phi negative 60 psi in that range of, you know, negative 120 to negative 60 is a right-handed alpha helix, or right-handed alpha helices. And this kind of lone bit with 60, positive 60 psi, about positive 60 phi, is a left-handed alpha helix. Helices. Okay. So the bit at the bottom isn't really talked about much. I truthfully don't know what it represents. But so I want to go into depth about each of these. So beta sheets are formed by hydrophobic interactions primarily, or rather I should say, are formed by interactions between two like amino acids. So either hydrophobic or hydrophilic interactions. I should expand that a little further. So they're usually something along the lines of, this is one beta sheet basically. So once you get to this point right here, what's going to happen is your protein is going to turn around and do the same thing again. So it's going to go back like that. And in this case, one sheet is pointed in one direction. So this is the N-S, this is the C-terminus of the sheet. On the other sheet, it's backwards, okay? And that makes this anti-parallel, okay? Because they go in opposite directions. Now, what if in that same situation, over here, we have, excuse me, it kind of loops back around a little bit with a bunch of other proteins and then starts again here. Excuse me for that kind of poor drawing. Well, in this case, we have the N-terminus, C-terminus, N-terminus, C-terminus. In this case, since they're both pointed in the same direction, this is a parallel beta sheet. Parallel beta sheet. And they do fold a little bit differently, but that's something that's, or rather, these are a little different. This unit, the reason that I didn't want to get too much into the weeds is it's things like how many angstroms is each pitch of an alpha helix or each turn of a beta sheet, things like that. And it's a lot of detail and a lot of math that I think is better suited for next week, simply because that's just all we'll be talking about next week, rather than having to talk about ESI and MALDI, which are also really big topics. Sorry, I heard a... So does the yellow region represent surface area? It's kind of like, how do I describe it? It's kind of like surface area. I would call it, I guess, almost abundance or prevalence, I guess. I don't know the exact word I would use, but it's kind of like, this is where we're likely to see these bonds exist, if that makes sense. Yeah, I'm sorry, I know that that's not the most fulfilling answer in the world, but it's, I don't know the exact word to use. But very briefly, I'd like to go into right-handed and left-handed helices. So your right-handed helix is, if you take your right hand, which I think on the camera it's my left hand for you, I'm going to I'm going to cup my hand and then I'm going to rotate it, like almost forward. So if, as I run, I'm rotating this way, that's a right-handed helix. So I'm rotating with my hand. It's a right-handed helix. And then the same thing with a left-handed helix. Hand into a cup, rotate forward. If it rotates that way as it's going up, then it's a left-handed helix. Okay? These two don't have too much kind of, they don't have a ton of like various numbers associated with them that are different. They tend to be fairly similar. I don't know if there are any properties even different about them, to be honest. But it's important to see kind of that right-handed helices are more common. And, oh, I'm not on OneNote. I was on Collaborate, so I couldn't scroll up. So, so are left-handed always vertical? The horizontal and vertical are the bond angles, remember? So when you say vertical, it's not that the helix is vertical, because I guess the helix could also be this way if you wanted to think about it. But it's that the bond angle psi is fixed at about 60 degrees. The bond angle phi can go anywhere from like, let's say 30 to 150 maybe, and this is just an approximation. Likewise with the right-handed helix, phi is kind of fixed around -60. Psi can be anywhere from -180 to -60, though it's more abundant in the red regions, so it's more common to see it maybe from -150 to -60. Things like that. But really good questions. So you'll also see Ramachandran plots, and I want to copy this one in because I think this is a better one, but unfortunately I didn't want to spoil just kind of what you'd see. And so let me add it in now since we're done with the Oh, okay, yeah, it's below. That's fine. So this is kind of what I think is a better Ramachandran plot because it has them all labeled, but also it kind of, I think it's smoother, and I prefer that, whereas this one is very jagged because it will be smoother. But so, I'm sorry, let me. So beta sheets, the alpha, or I'm sorry, the parallel and anti-parallel really affect their qualities. Not a ton, but like it affects, for example, the length of each interval. So how this beta sheet goes there and then it turns up and then down. It affects how many amino acids, the length of each of those. I think they're called. I don't remember the name. I need to look that up again. Alpha helices tend to be fairly consistent regardless of whether they're right-handed or left-handed. And a large part of that is that it's effectively the same thing. It's just what's easier for the protein to fold into based on the things that it's got attached to it. So, and that's also why there's a bit of variance, by the way. The angles aren't fixed because, for example, if you've got something like tryptophan, well, in the case of tryptophan, let's see, so you've got your central carbon, you're probably going to have your C-terminus almost like that and your N-terminus like that since tryptophan is massive, right? On the other hand, if you've got something like glycine or alanine, well, even just hydrogen there, hydrogen here, well, they can go kind of a little bit more flexibly. And so depending on the variable R group, that's kind of why there's such a wide range of bond angles that are able to be used, because the R group kind of changes how flexible your bond can be, in addition to just the bonds can naturally kind of move around a little bit and will move around a little bit depending on the polarity of the things around them, things like that. Okay. And I want to show number, I think, 15 again, just to make sure that I'm thorough. So what does the Ramachandran plot tell you? It tells you which secondary structures are present. So one kind of, I don't want to call it a weakness, but one kind of thing to keep in mind is it doesn't tell you how many. So if you've got a protein that's 500-600 amino acids long, well, we could have an alpha helix at the beginning, and then another alpha helix, and then another alpha helix. And if they're all right-handed, I'd only ever see the spot here in this area. If I have one right-handed, one left-handed, and then another right-handed, I'd see two spots. And so it's important to keep in mind that these don't tell you the abundance of each. They just say you have a right-handed helix. It also doesn't tell you how long the helix is. Your right-handed helix could be 30 amino acids, it could be 20, it could be 50. It doesn't get too large, but it can have varying sizes. And so that's another kind of thing to keep in mind with the Ramachandran plot, is they don't tell you everything. Any more questions? Okay, awesome. Well, I'm going to go ahead and stop the recording. Thank you so much for coming, and have a great week. Hope I see you next week.